Okay, so hello everyone, and welcome to this session on machine learning with and for software engineering, number 6. So for this session, we will have 6 presentations. We will have there will be presented one after the other, and we will be having the discussion period after all the presentations. But if you have any quick question or just clarification after presentation, so we can accept like one quick question or clarification and keep the rest of discussions at the end. So we will start by the first presentation on the paper titled Deep FD, Automated Fault Diagnosis and Localization for Deep Learning Programs, that will be presented by Jaloon. I hope I'm pronouncing
Hello.
correct your name.
Yes, you're correct.
Okay,
Thank
that's
you.
great. So yeah,
Yes.
please
So may I
go
share my
ahead.
screen? Okay. So can you see my screen now?
Yes, that's
Yes.
great.
Okay.
Okay, please go
So
ahead.
that's okay. So let's start. Hello, everyone. It is my great honor to introduce our work, DeepFD, Automated Fault Diagnosis and Localization for Deep Learning Programs, to all of you. Before I start, I would like to introduce the cooperators from 5 institutions. It is a great honor to work with you. So let's get started. As deep learning systems are widely used in our daily life, how to automatically debug such systems become essential. So our work is designed for debugging DL systems. It is a learning-based fault diagnosis and localization framework. Saying learning-based, it is because we regard the fault diagnosis problem as a multi-label classification problem. It learns to distinguish the normal and buggy DL models according to their runtime features. It goes beyond the bug detection. It can also diagnose the root cause of the faults and pinpoint the faulty lines in the program. The secret of DeepFD is that some runtime information exhibits significant correlations with certain types of faults. For example, the figure shows the distribution of several features when the learning rate and loss function are faulty, painted in red, or not faulty, painted in blue. We can observe that there's obvious statistical difference when the learning rate or loss function are set appropriately or not. The observation enables us to perform fault diagnosis and localization as a learning problem while leveraging the relevant stochastic runtime information of a buggy DL program. Based on this idea, we then zoom out to a bigger view. Is the whole picture of DeepFD. The upper part is a workflow of DeepFD, while the lower part is a preparation steps for it. We skip the details of the lower part and briefly introduce the upper part. The workflow of DeepFD comprises 3 steps. Given a program, DeepFD constructs a DL architecture and collects a runtime data such as the loss and neurons informations by training the DL models. After applying a series of statistic operators, the diagnostic features are produced. Then we infer the possible types of faults using the pre-trained diagnosis models prepared by the lower part in the previous slide. And since there are usually more than one faults in a program, so we adopt the multi-label classification models so that one buggy program could be assigned to more than one fault types. Finally, it goes through the nodes of the parsed abstract syntax tree, traverses assignments and expressions, and identifies the lines where the diagnosed types of faults are defined. Note that currently the diagnosed models are trained to classify 5 major types of faults, including unsuitable loss function, optimizer activation functions, insufficient training iterations, and the inappropriate learning rate. We made it extensible for supporting more types of faults. We also constructed a benchmark with 58 buggy DL programs from Stack Overflow and GitHub. The benchmark includes 40 programs, the patches, usually more than one, the types of faults, and line numbers where the faults are introduced. The left-hand side shows the number of each type of faults in the benchmark. And highlighted in yellow, we can see that the top 5 types of faults account for more than 70% cases. This is the reason why our current DeepFD are designed to debug these 5 types of faults. In addition, we further present the statistics of the number of faults type in blue and number of faulty lines in red. We can see that over half of our program contains more than one fault type, and most of them involve more than one lines. And this observation motivates us to adopt the multi-label classification algorithms. In conclusion, DeepFD maps the fault localization task on DL programs to a learning problem. We also constructed a benchmark for future fault localization works. The work encapsulates the fault seeding, faulty program checking, feature extraction, fault diagnosis and localization, and it has been made online available. That's all for our presentation. That's all for the presentation. Thanks for listening. All questions and cooperations are welcomed. We are glad to hear from you.
Thank you very much, Jalu, for this very nice presentation. So our next presentation will be named for the paper Fast Change Set Based Bug Localization with BERT will be presented by Angeniska.
Okay, hello everyone. Let me just
Hello.
screen. Okay, so let's start. The title of the paper is Fast Change Set Based Bug Localization with BERT. So in this paper, we propose a bug localization tool that focuses on 3 things. First, we want to locate bug-introducing change sets, since change sets are typically easier for developer to examine, and they also contain other useful information, such as change set log or a timestamp. Secondly, we want to capture semantics of input documents. And finally, a fast retrieval, and this essentially means we want to quickly localize relevant change sets and minimize the time a developer has to wait for the result. So to address those 3 requirements, we propose FBL-BERT. FBL-BERT uses BERT to capture semantics and late interaction architecture that enables efficient retrieval. So how it works? First, the model processes bug report and a change set separately through BERT and linear layer, and then it creates a matrix for each of them. Next, for each word vector in a bug report, we look for the most similar word vector in a change set. Then we sum the cosine similarities between the most similar pairs, and we have our final score. There are 2 main advantages of this approach. So first, it preserves information at the level of words, which should help in capturing explicit code tokens in a bug report. And the other thing is that the model is optimized toward maximum similarity of vectors. And this means that we can find potentially relevant change sets based on whether they have similar word vectors to our bug report. So in practice, using FBL-BERT consists of 3 steps. First, of course, we train the model. Secondly, we take all of the change sets and encode them with the trained model. Then we put the encoded change set into an index. Preferably, the index should support efficient vector similarity search. In our case, we used FICE. And finally, we have our last step, that is retrieval. So when a bug report arrives, it is first processed by FBL-BERT. And then we do exactly the same thing as we did during the training. So we will take every word vector from a bug report and ask the index to give us the most similar word vector in a change set. Our goal here is to find let's say top 1000 good candidate change set, which have similar word vectors to our bug report. Having that, we will now use the pipeline to actually re-rank only our good candidates. So in this table here, we show retrieval accuracy measured with mean reciprocal rank. As our baseline, we use Locus, which is a vector space model, and 2 T-BERT models, which are recently proposed deep learning models, also for change set retrieval. Overall, we can see that FBL-BERT performs better than Locus and both T-BERT architectures. However, the question is why and when. So we decided to look into results for different types of bug reports. We have not localized, partially localized, and finally, fully localized bug reports. Looking at the results for not localized and partially localized bug reports, we see that all BERT-based models perform better than Locus for not localized bug reports. For partially localized bug reports, so the second column, Locus improves. However, it still stays behind BERT models. Looking at the results for fully localized bug reports, one may ask a question why the performance now drops for both T-BERT models and also our FBL-BERT. We decided to get a better understanding, and we did an error analysis. We observed that very often a bug report that is fully localized contains a few stack traces or code snippets. In case of FBL-BERT, it leads to the model being basically flooded by code tokens, so that the model is struggling to decide which code token is important, which in the end affects the final performance. All in all, we can say that we see improvement in retrieval accuracy when using FBL-BERT. However, it works best for bug reports that have no or a few class mentions. Let's also look at the time that is required to retrieve relevant change set. In this figure, we can see the retrieval time per one bug report given different sizes of a search space. Here we see that FBL-BERT, that is marked with squares, retrieves relevant change set faster than both T-BERT models. Another thing is that while for T-BERT models, we can see that the retrieval time increases as the search space grows. For FBL-BERT, the trend line flattens, so it indicates that the model scales up well with respect to growing number of documents. And a confirmation also of this statement is visible in the table on the right, where we can see how each of the models scales depending on the number of documents that we are looking through. And that is all. Thank you.
Okay, great. So you are in time. Thank you very much for this very nice presentation. Any quick question or comment? Otherwise, we go to the third presentation of the paper titled Multilingual Training for Software Engineering that will be presented by Tawfiq. So please go ahead.
Thank you. Give me a minute. So can you see my screen?
Yes.
Okay, thank you. So today I'm going to present our recent ICSE paper, Multilingual Training for Software Engineering. I'm Tawfiq. I'm a fourth-year PhD candidate from UC Davis. This work was done by me and my advisor, Professor Prem Kumar Devanpo. So modern deep learning models have millions and billions of parameters. It is very difficult to train such model with limited amount of training data. So in this paper, we propose a novel approach to augmenting the training data set. So these are the motivation of our work. As you all know, data creation or curation is a slow and effortful process. It always requires some form of human involvement to generate the data. And we have also seen that for some languages, like Ruby, the label dataset is not that abundant. And for some languages, the data may be more domain specific. We also found that most of the, for several deep learning based, for several software engineering tasks, the performance of the deep learning model depends on identifier. And identifiers are not language specific. That mostly depends on the algorithm. So if you are implementing an algorithm in multiple languages, there is a high possibility that you will use the similar set of identifiers. So these two findings inspired us to investigate the potential of multilingual fine-tuning in software engineering tasks. So we tried this idea on 3 popular software engineering tasks. Let me introduce you to the task first. So the first task was code summarization or code comment synthesis. The second one, code retrieval or code search from natural language description. And the third one, extreme summarization of method name prediction. For all these 3 tasks, we use CodeSglue dataset, which is a modified version of CodeSearchNet. This dataset is multilingual and the data comes from 6 different languages, Ruby, JavaScript, Java, Python, PHP, and Go. So multilingual training is not a very new idea. There are several papers in natural language processing domain that have reported that it is very beneficial for low resource languages. So the benefits are observed in 2 situations: when the language are low resource and the language are related to each other. So we have a very similar situation here in CodeSglue dataset. For Ruby and JavaScript, we don't have enough samples to train a model properly. And we also believe that these languages are related to each other by the identifiers. So we look into that we'll look into some research question about that in the later part of my presentation. So there is another advantage of using multilingual trained model. So when we are replacing a monolingual model with a multilingual one, we are actually replacing multiple models with one. So deploying multilingual model is more practical and easy. So I have talked about two basic idea that inspire us to apply multilingual training in software engineering tasks. And we have two research questions. The first one is, what role do identifiers play in code summarization tasks? So when we abstract out the identifier in code summarization task, we observe that the performance of the deep learning model drops a lot. But when we abstract out the other tokens like keywords, the operator, and the separators, the performance does not change that much. And the second research question, do programs that solve same problem in different languages tend to use similar identifier names? We use Rosetta code that provides us multiple implementation of the same algorithm in different languages. And from that data set, we also observe that like for a similar algorithm, people tend to use same set of identifiers. So please look into our paper if you are really interested about these two research questions. So in this slide, I will introduce you to the metric and model we are using. For code summarization, we are using CodeBird and GraphCodeBird, and the metric is BLEU4. For code search, we are using the same two models, and we use the mean reciprocal rank as the performance to measure the performance. And for the method name prediction task, we have F-score. So this is the performance what we achieved using multilingual training in code summarization task. So these two columns presents the monolingually trained models performance. So for CodeBird, we achieved 17.83, which is exactly same as the number reported in the original CodeBird paper. And for GraphCodeBird, we achieved 18.08 with monolingual training. With multilingual training, the performance goes up. For polyglot CodeBird, we achieve 19.06, which is 6.90% more than this original CodeBird paper. And for the polyglot GraphCodeBird, we achieve 19.10, which is 5.64% more. So note that for the low resource languages that I already mentioned, Ruby and JavaScript, the performance improvement is higher. For CodeBird, we can see like 17.72% improvement for Ruby with multilingual CodeBird and 14% for JavaScript. And for high resource languages, that the language which has more than 150,000 examples, we have also seen like 2 to 4% improvement also there. So this is the table that compares the performance of our models with the state of the arts during the writing of this paper. So we can see that our polyglot CodeBird and GraphCodeBird outperforms the other models by significant margin. As I already mentioned, we have tried this multilingual training in 2 more tasks. For code search problem, we observed 2.74% improvement with the CodeBird model, and with multilingual GraphCodeBird, we observed 1.54%. And for this method name prediction task, we have 10.09%.
Sorry for interrupting. So can you like conclude? You exceeded the allowed time, please.
Yes. So let me summarize the overall contribution of our work. So we showed that identifier name choice is well conserved across languages. That means identifier mostly dependent on the algorithm, not the programming language. We also showed in a paper cross-language training helps. So if you have a larger data set on Python and a smaller data set in Ruby, if you train the model with Python data, that may help the Ruby data set. And the identifier matters more in the training data. Identifier matter more in training data in code summarization task. We have a research question to support this statement. And finally, we showed multilingual training data improves performance on several tasks. So thank you.
Okay, thank you very much, Tawfiq, for this nice presentation. Next presentation will be on paper titled Neuron Fair, Interpretable White Box Fairness Testing through Bayesian Neuron Identification, that will be presented by Haibin.
Thank you. My name is PhD candidate of Zhejiang University of Technology in China. The paper I will be presenting today is titled Neurosphere. Nowadays, algorithms provide us with convenience, but the issue of bias in the decision-making process cannot be ignored either. Several institutions are also committed to the realization of deep learning fairness. The existing fairness testing method can be divided into three types. The first is testing method for traditional machine learning. This method cannot be applied to deep models. The second is method for traditional machine learning, but can be applied to test DNNs after modification. The third is method specially designed for DNNs. These works are limited in practice due to at least one of the following reasons: can hardly be generalized to unstructured data, challenged by gradient formation, hardly provide interpretability. Okay. Here we give the basic knowledge. The first is data form, the second is discriminatory instance determination, the third is the discrimination analysis based on decision boundary. Then we introduce the motivation. First, the decision results of DNNs are determined by nonlinear combination of each neuron's activation state. Thus, we imagine whether the biased decisions are caused by some neurons. Secondly, we try to observe the neural activation state in DNN's hidden layer through fading instance pairs. Third, we automatically identify biased neurons. Okay. Our design goals and solutions are as follows. Neurosphere contains three main steps. The first, according to the previous definition, we draw the AS curve of each layer. Yes. Next, the layer with the largest AUC value is selected as the most biased layer. Finally, we adaptively identify biased neurons. The discriminatory instance generation includes a global phase and a local phase. The global phase is increased the diversity. Here we use momentum-based accelerated search. First, determine the search direction and then add perturbations. Repeating this operation for the remaining instance. Okay. And the discriminatory instance obtained in the global phase are used as a seed for the local phase. Similarly, we use an instance as a seed. Then determine the search direction and then add perturbations. Repeat the operation. And step 3 is instance generation on unstructured data. We first leverage adversarial attack to generate sensitive attributes perturbation. Then we craft the biased perturbation. Finally, we add both to original phase image. And this is dataset information. These are baselines we adopted. These are metrics and parameter setting. We evaluate Neurosphere by answering 5 research questions. Okay. First, Neurosphere generates more instances than baselines, especially for densely code structured data. Okay. A Neurosphere generates much more instances than our baselines in the global phase, which is beneficial to increasing the diversity of Neurosphere's instance in the local phase. Next, the Neurosphere is robust to the hyperparameters. The GSR value of Neurosphere are higher than that of baselines on almost datasets. In our case, it can generate more diverse instances. The instance generated by Neurosphere contribute more to fairness improvement. This is a summary. Second question, neural-fair is more efficient in generation speeds. The main reason for its utility is that its instance can activate more biased neurons. In our case, AUC can correctly distinguish DNN's fairness violations. This is a summary. Okay. The final question. Among image data, image instances of neural-fair are of higher quality. The generated test instances are similar to the seed inputs. Neural-fair contributes more to the fairness improvement of the face detector. This is a summary. Okay. In conclusion, we propose neural-fair. It performs well on interpretability, efficiency, and generalization. We conduct detailed experiments to evaluate the performance of neural-fair on 7 real-world datasets. Finally, we systematically analyze neural-fair from 5 aspects. And thank you for your attention.
Okay, thank you very much, Haibin, for this great presentation. We have the next
Thank you.
presentation on the paper type for PI, practical deep similarity learning based type inference for Python, that will be presented by Amir.
Hi everyone, can you hear my voice?
Yes, we hear you.
Can you see the slides?
We see the slides. Can you make full screen?
Yeah,
Present
of course,
remote?
of course.
Okay, that's great.
Yeah, hi everyone. My name is Amir Mir. Today I'm going to present Type4Py, our technical paper at XC22. As we know, Python is easy to use and it allows rapid prototyping. On the other hand, due to the lack of static types in Python, developers often encounter type errors like this example. And Python, of course, supports for optional type annotations, meaning that developers can add type annotations gradually to their code base. However, this is a daunting task, and motivated by this, researchers have recently proposed ML-based type prediction models, and there are some static type inference tools also for this task. In this space, ML-based type prediction, we have identified a challenge and a problem. The main challenge is that to suggest the correct type in the top one is very challenging for the ML models. I mean, as we know, the ML models usually give a list of predictions. It could be top 5 or top 10. And also, research has shown that developers tend to use the first suggestion by a tool, so it would be very desirable for the ML model to give the correct prediction in top 1 or in the first location. Also, the main problem that we identified in this space is that developer-provided type annotations are not always or may not always be valid for training and evaluation. And therefore, it is essential to type check the data set to make sure at least the evaluation set is valid for evaluation. In this paper, we present Type4Py. It is based on deep similarity learning and hierarchical neural networks. And part of our contribution is to have a type check data set. And also we have a Visual Studio Code extension, which provides ML-based type auto-completion for Python. Now I would like to talk about our proposed approach. This is the overview of Type4Py. First, we extract abstract syntax trees or ASTs from Python source code files. And from ASTs, we extract features like identifiers, code tokens, and visible types in order to predict types. Next, we extract token embeddings from the extracted features. And in the model, we have in the middle, we have a Type4Py model. And at the prediction phase, we have the learn type clusters to suggest types for test samples using k-nearest neighbor search. I have one code snippet here to explain the type hints or features that we use to predict types. We have visible types, which is extracted from import statements from Python files and their transitive dependency set. We also extract identifiers from code like function name, parameter names, or variable names. We also consider code context, which is the usage of parameters and variables inside the function body, like shown in this example. This is a Type4Py model. It consists of two RNNs, or recurrent neural networks, with LSTM cells. And we also have a final linear layer that produces type embeddings for type clusters. We have extended our many Type4Py data set for this work, and we perform coded application, which is an essential step. We augmented our data set to add more variable type annotation using Pyre, a static type inference tool. Last but not least, we perform type checking using MyPy to make sure that source code files are type checked and our ground truth for both training and evaluation are valid and type correct. Now I want to talk about the evaluation of Type4Py. In general, we have three research questions. The first research question is about the general performance of Type4Py. Due to the time constraint, I only present the first research question. Considering the top one, an exact match, Type4Py achieves around 76%, which is significantly better than both state-of-the-art approaches, Typeless and typewriters, as we can see here. Also, considering the MMR score, Type4Py again outperforms both approaches. I also want to talk about Type4Py deployment in practice. This is the deployment of Type4Py. We have the Visual Studio Code extension, as I said, for developers at the client side. We also have a production models on our Kubernetes clusters. We also provide a local model for developers for privacy reasons. This is the VS Code extension. As of now, it has more than 1,100 installation. This is one example from the Visual Studio Code environment that it provides ML-based type auto-completion that developers can use to gradually add type annotations to their Python code bases. To conclude the work and consider the future work, maybe using pointer networks can be a promising direction. Also, we would like to study how to improve Type4Py from its usage in VS Code and the telemetry data that we have. Also, complementing Type4Py with a static type inference might be also a promising direction to try for future work. And we also made our code and dataset available on GitHub and Zenodo. And yeah, that's it. Thank you so much for your attention and joining this session. And I'm also available for the Q&A session.
Thank you very much, Amir, for this beautiful presentation. And now we are on the last presentation for this session on the paper titled Decomposing Convolutional Neural Networks into Reusable and Replaceable Modules that will be presented by Ranjit.
You can see my screen?
Yes, we can see.
Thank you. Hi, everyone. My name is Ranjit Pan. I'm a fourth-year PhD candidate at the Iowa State University, and I'm presenting our work with my advisor, Ridesh Rajan. Today, I'm going to tell you about an approach to decompose convolutional neural network into modules to enable the reusability and replaceability. We envision that decomposing model into modules can help to solve real-world problems. For instance, in the past, Google Photo tagged a black woman as gorilla. Not only that, recently Facebook, and known as Meta, also had a similar instance where a black man has been labeled as primates on a video. While we do not have the information how Meta resolved the issue, we found that to resolve the similar issue, Google has decided to remove the output class gorilla by suppressing the output level. In fact, they have suppressed the output for chimpanzee, monkey, chimp, etc. from the model that recognize a wide range of images, for example, car, human face, etc. Though the problem can be temporarily solved by suppressing output level, to fix the model, one needs to retrain the model. Suppose we can decompose a CNN model into modules, one for each output class. Also, suppose we have another working model trained with the same or a subset of dataset with gorilla and person output class. and if we can decompose, and also the latter model does not exhibit the behavior present in the faulty one. Then we decompose the model and replace the faulty Gorilla module with the working Gorilla module that does not exhibit the incorrect behavior. Other solutions include creation of small model and use it as a module. Or we can remove the Gorilla module from the collection, which is similar to what Google did to resolve the problem. We introduced the notion of the decomposition in our previous work published in Secretary 20. We proposed an approach to decompose the dense-based deep neural networks into reusable and replaceable modules. However, that work focused on dense-based networks, did not explore more complex set of models such as convolution neural networks. That work relies on the dense architecture of the models where nodes and edges have a one-to-one relationship. In contrast, edges in CNN are shared among all the inputs and outputs. Also, prior work performed backtracking mechanism to decompose the module, which is only applicable to the dense space layers. Our approach starts with a trained model. For instance, in this case, a model that recognizes image level as A to D. First, our approach identifies the section in the CNN that is responsible for a single output class. Since removing nodes for all the non-constant output class, the modified section acts as a single class classifier. To add the notion of the negative output classes, we add a limited section of the inputs from the unconstant output classes. Finally, we channel the constant to create a module. In this context, we use constant and unconstant as terminology that represent the input belonging to the output class for which a module has been created, and all other output classes respectively. For example, for module A, output class A is the constant output class, and other output class such as B, C, D are the unconstant classes. We answer 3 research questions. Does decomposition involve cost? How modules can be reused or replaced to build new problems compared to training a model from scratch? And does reusing and replacing modules emit less CO2? Overall, we found that there is a cost of decomposition, but that is trivial. Also, we showed that possibility of reusing and replacing modules. Also, we found that for all cases, composed models using modules emit less CO2e compared to the training model from scratch. To that end, we propose an approach to decompose convolution neural network for image-based classification problems into modules, one for each output class. We show how real-world issues, such as issues that Google and Meta faced earlier with incorrect classification, can be addressed by decomposing a model into modules instead of training from scratch. We discuss the methodology, a 3-step process taking the monolithic model as input. The output is a series of modules that is a binary classifier. We answer 3 research questions that's related to the cost of the decomposition, the possibilities of reusing and replacing the modules, and the consumption of CO2e in reusing these modules compared to the model trained from scratch. We made the preprint available, and also our longer video is available in the Confluent Researcher, where you can find more detailed description. Thank you.
Okay, thank you very much, Ranjit, for this very nice presentation, and thank you all presenters for this awesome, and congrats again for having your papers published in EXE. So let us have session of questions. I think there are already so many questions in the chat box. So first question for Angeniska, I think she already answered in the chat. There is also one question for Tawfiq. Did you look at tasks where a single snippet can contain multiple languages, such as Julia embedding a MATLAB snippet, for example, thinking in terms of either summarizing such methods while considering both languages involved, or code completion that can switch between languages? So it's for you, Tawfiq.
Actually, in our paper, we have not tried such approaches yet, like using a single snippet that can contain multiple languages. But from my experience, I believe that if you have a few examples of such type, then this multilingual training can help for at least code summarization task. So I'm not sure about this code completion task because that is not identified heavy. That is more dependent on the syntax. And when we do this multilingual training, it is difficult to say that we can perfectly generate the code, do the perfect code completion task with multilingual training. If we are asking for some partial completion, that is, I think, possible. Thank you.
So thank you, Tufik, for your answer. I think there is another question for you. Have you done any work on zero-shot summarization or other tasks on another low resource language that was not included in the pre-training, like R?
In our there was in the original code but paper that was evaluated on C#, and they got good results. So for our work that is, so we are doing multilingual training, so we have a big data set. So our decoder is stronger. It is like trained to generate a natural language description. So I believe if I'm not sure about the zero-shot training, but with a few samples, like maybe 10 to 15, this multilingually trained model can give you, I think, reasonable summarization on the deduplicated dataset.
Okay, thank you, Tufik. Then there is another question for Ranjit. How is the robustness of the decomposed modules against fairness or attacks?
Jinju, that is a really nice question. And for at least this work, we did not study the robustness or the fairness or the attacks. However, what we believe that the decomposed modules are similar as the decomposed module, decomposed software. They should have the same traits or the properties that the parent has. Since the reason is that since they are decomposed to enable reusability and replaceability, that was our goal to achieve. We decomposed in vertical way, and so if there are properties that is present over all the models, layer wise, and we believe those properties will still be present in the decomposed model. However, it needs further investigation. And in fact, there's a very nice line of work you proposed. Definitely, I will personally look into that.
Okay, thank you, Ranjit. Do you have any other questions or comments? Even from presenters, you can ask each other questions.
I have one question for Jialun, if I'm pronouncing that correctly. First of all, that is a really nice work. So I have two questions. First one is that you said in your paper that there's a significant number of bugs you found there, where a significant number of programs you found where there are more than one bugs. So
Yes.
are the programs being found from the real world? Because I did a study with other co-authors back in 2019 where we found different Stack Overflow bugs and classified the deep learning bugs. But we mostly found the bugs, code has a single bug. So my question is that, let me refresh. So how often do you find that there are programs where more than one bugs are present in the real world code?
Okay, so may I share the screen? Okay, so maybe I can share the screen.
Yes.
No? Okay.
We do not see your screen, Jialun.
Okay. I need to find my slide. Okay, here. Okay. So can you now see?
Yes, we
okay.
see your screen now.
So you mean this one, right? So we can see from the right hand side the statistics. They're actually 24 over 58. Like half of the programs are tens one types of fault. Yes, which equals the result that you you concluded before, but after we when we reproduce and compare the programs, we not only use the accepted answers in the Stack Overflow, we also try out all the answers that's suggested. And sometimes we find that there are other bugs in the program, not only the accepted answers. So that's maybe the reason why we found more bugs in that program.
Yes, and thank you for answering that. In fact, I have a follow-up question. Since you said there are multiple bugs, can it be done by, there are works that localize and fixes single deep learning bugs? Can we run those tools multiple times to fix multiple bugs? For example, a code that has 3 bugs. Can we run, for example, a tool X run first time, it fixed the bug 1. Then once it fixed, we found the bug 2. We ran the tool again. And if init number of instances run, can it be done by that way too? And did you see if there any application of such approaches?
Yes, it is possible. So that's the reason why when we run the debugging, we run each DL programs 10 times and collect all the results, and we take the union of the diagnosed types as the final results. Yes, so the situation you mentioned also happens a lot of times.
Thank you, Jalon. Thank you,
Thank
Franji,
you.
for the
Thank you.
question, for the answer. Do you have, guys, any other question or comment from the audience, from presenters? So otherwise, maybe I can have one comment on or one question to Jalon. So you have multiple classes for these kind of bugs or defects. So I'm wondering your ground truth. How did you get it, and how did you validate it? The classes. Did you do some manual labeling or validation for your data set?
So may I share my screen again?
Yeah, go ahead.
Yes. Okay. So for how we collect the benchmarks and how we manually construct it, so we can see here, since the programs or the code snippet in the Stack Overflow and the GitHub, they did not actually provide the actual repair. So we manually reproduce all the bugs, whether it's runnable complete and whether the bug symptoms matches the description. If so, we will further apply all the patches and try to repair the programs. So this process involves manual labeling, and we will repair to confirm whether the fault types are really faults in that program and whether the patches will really fix the bug.
Yeah, and so when you do debugging, so since the deep learning programs are stochastic, sometimes
yes.
you don't get the same execution. So did you get any trouble with that when reproducing or debugging the code, reproducing the bugs?
Yes, the stochastic will introduce several problems. The first, sometimes the accuracy will ranges from like in a large range. So we for every repair and every buggy programs will run it like 10 times. Need 10 times to get the average result. So it to reduce the randomness impact. And second is that after repair, how can we ensure the patches is actually the patch? So for that, we can. It should be here. So for here, to validate whether a patch is actually the patch, we will check whether there is a statistical difference between the accuracies from the buggy program and the corrected programs. So there are two difficulties.
Okay, thank you very much, Jalon. Very interesting work. So that's why we had many questions on that. Actually, all papers are very, very interesting. So do you have any other questions or comments from the audience? We still have time. Otherwise, I can have a quick question for Ranjit. So how do you measure your model reusability and replaceability? Is there any systematic way to measure them?
So when we measure the efficiency or reusability and replaceability, we compare with a from scratch. For example, we have, I'm taking the example from our previous paper. So yes, we have a model MNIST that recognizes digit 0 to 9. And we decomposed a model, decompose that model into modules for each output class, 0, 1, 2, and so on. There may be a reuse scenario where we need to build a binary classifier. We take the 0 and 1 module. We make a composed model using those modules. And on the other hand, we train a model taking the example of 0 and 1 and measure the accuracy. And we compare the accuracy and understand whether there's loss or gain. And if there is a loss or gain, what is that? We do the same for both reusability and replaceability. Does that answer your question?
Yeah, thank you. Thanks, Ranjit, for your details. Maybe you can have one more question.
I have one question actually for Tawfiq
go ahead,
regarding
please.
the CodeBERT. I was just wondering whether there might be some data leakage in using CodeBERT for fine-tuned tasks. I mean, as we know, CodeBERT was trained on big data set with multiple languages, right? So
Yes.
if you train CodeBERT on a fine-tuned task, let's say code summarization, then would there be some, let's say, the data leakage or some chance of some data leakage for the fine-tuned task?
Okay, there are several aspects of this. Like the code search, the code exclude data set is actually prepared in a way like the training test and validation. They use the same splits for the pre-training and both fine-tuning of code summarization. So if at least we are assured that the pre-trained model has not seen the test data for the summarization task. And regarding this like cross-lingual clone, this is that is not well studied yet. Like when we mix these languages for like Python and Java, there can have some clones, but that is not we are not sure yet. But there is no exact matches because the syntax is completely different. So we are pretty much sure that there is no exact leakage, but yeah, it can happen to some extent.
Okay, so thank you for the answer.
Okay, great, thank you. Any other questions?
Tawfiq, I have one question. So that was really nice work. So I mean, if I understand correctly, you are proposing a multilingual model. And my question is that whenever there is a new language, do you need to train the model again? And if that is the case, and is there any way you can build something language agnostic mode?
So for the summarization task, we believe like these new models like the Code-T5, which is like came after our work, and also the work we are presenting here, like this multilingual CodeBERT and GraphCodeBERT. This multilingual CodeBERT and GraphCodeBERT, if you take this model and fine tune on a few samples, like maybe 15 to like 20 data, that will give you, I believe, very good results. The Code-T5 will not. We have done some experiment on that because the decoder is not trained to generate natural languages. So we need like 150 to 200 data to make it work, the Code-T5 one. So if a new language came, I would say if your decoder is trained to generate natural languages like PL-BERT and this multilingual CodeBERT, maybe only a few languages enough to achieve good results. But it's all experimental. If the language uses very different set of identifiers, then we may need more data. Yeah, thank you.
Thank you, guys. Any other questions, comments? We still have a few minutes. Let me maybe have one quick question to Agnieszka on, so I appreciate the extensive experiments that you have done comparing your work with the baselines. So I'm wondering if there are any specific situations where your approach is more successful than others or less successful. So when looking at the results, is there any like specific situation that catches your eyes?
Yes, so we actually did an error analysis on our model. So we discovered that in the case of our very particular architecture, what matters the most is the number of code tokens that can overflow our model, so it can struggle with a lot of code names. And that was the time when we saw vector space model doing extremely well. So overall, we saw that those supervised architectures, like our model FBL-BERT and also T-BERT models, they do better when they do better for not localized bug reports. So those are the bug reports that have no mention of like any class, very natural language description. So those models perform better for such bug reports, also for partially localized bug reports that have little mentions of classes, and then for fully localized bug reports that mention a lot of different code tokens, typically vector space model works best.
Okay, great. So thank you very much. Any other questions? Otherwise, let us wrap up the session. So I would like to thank you again for your nice presentations, also for the participants. Thank you for attending, for your questions, your comments. I'm glad to be chair of this session, and so now we will be closing this session, and enjoy the remaining sessions of ICSE, and see you around. Thank you very much.
Bye.